Okay, so now we continue the course talking about dislocations. And dislocations have been mentioned many times during the course already, but now it's maybe a good time to go into detail of what they are and the basics of dislocation properties. Well, dislocations are per definition line-like defects in a material. So a line-like means that basically you can draw a line which follows the dislocation. As you can see in this image, they can be curved. The line doesn't have to be straight at all. It can be a complex three-dimensional pattern, but still the center or the core of the dislocation is line-like. Of course, in reality, all materials consist of atoms, but as we shall see, this core is really only a few atoms thick. And the reason they are very important, also completely independent of irradiation, is that they exist in all metals and many other crystals as well in equilibrium. And actually, the mechanical processing and shape of metals, shape change of metals is usually completely dominated by dislocation effects. But the reason these are also relevant to irradiation is that irradiation often generates dislocations and can modify the mechanical properties of the materials. And actually, when you have high dose radiation damage in metals, the dominant effect is all by dislocations. This is actually also true at high temperatures in semiconductors. For instance, in silicon, if you go above 300 degrees C when you irradiate silicon, silicon never amorphizes, just like metals, but you do build up defects and dislocations in silicon as well. Well, to give a brief overview of how dislocations can be generated by irradiation, you can say that there are 2.5 ways of doing it. First of all, you can generate dislocations directly in dense heat spikes, and then they can collapse into a dislocation loops, and these have been described earlier in this course. The variety of this is that quite often a heat spike generates a fairly complex vacancy or interstitial cluster, but then when you give it time in thermodynamic equilibrium, these vacancies or interstitials quite often reform into a dislocation. Also, when a new cascade overlaps previous damage, you can form dislocations. The other variety is that irradiation can create small point defects or small clusters, and these can be mobile and later on coalesce into a dislocation loop. The dislocation loop means something shown in this picture here, dislocation which curves up on itself, and then you have a loop-like roughly spherical feature. Already mentioned in the previous sex, this dark contrast here is the strain field of the dislocation. The dislocation is very small, itself is very small, and it's the center of this loop-like feature. The reason they don't look circular is that they can be oriented in different ways, and then in different projections they look different. The reason this happens is that in most cases, a dislocation, if vacancies or interstitial coalesce into a dislocation, the energy of this structure is less than a set of independent interstitials or vacancies, so it's energetically favorable to form them. Now, before we continue the radiation properties, we go into good detail of the basics of dislocations. So as I said, they are per definition line-like object, and the dislocation core is only a few atoms wide. However, you can see them as much bigger objects by doing etching. That is, if you take a metal with dislocations and then start doing certain varieties of chemical etching for removing atoms from the surface, it turns out that if you have a dislocation, the atoms around the dislocation core etch more efficiently, and this etching pattern spreads, and then you get pits on the surface where the dislocations are. So this here is an image of a metal that has been etched, and each pyramid-like looking like feature here is shows where a dislocation is. So the dislocation core is at the center, and this etch pit has then formed around it. And this variety of scene dislocations has the major advantage that once you do this, these can be pretty big, so big you can see them in optical microscope, and then you can get the dislocation density simply by counting how many of these edge bits you have, and then you can get a dislocation density, which is number of dislocations per area. If you have regular point defects, the point defect density is defects per volume, but because dislocations are line-like, the dislocation density is always given as dislocations per area. Well, so this was the easiest way to see dislocations or find dislocations, but this doesn't tell very much about their structure because you only see this edge bit. But in transmission electron microscopy, where you take a metal or any material sample, make a thin filament out of it, and then image through the sample, you can see dislocations directly. And this here is an image which would depend on what kind of screen you are. It may be better or worse quality, but basically you see darker line-like features here. For instance, if I track here, here is one darker line-like feature, and this line-like feature here is a dislocation, or actually this what we see is always a two-dimensional projection of the three-dimensional dislocation inside the material. The lower image also shows a set of dislocations. These are mainly dislocation loops and a helical dislocation pattern which has been formed in aluminum magnesium alloys after rapid cooling. Basically what happens in this rapid cooling is that initially at high temperature you have a big number of vacancies, but when you cool then the vacancies coalesce to dislocations. But the nice thing is that in TM electron microscopy, transmission electron microscopy, you can, if you have a suitable temperature and, for instance, strain the sample, you can actually also see the dislocations move. So this now, when I started this animation, if you look closely, you see that there are some of these, not all of these, but some of these dislocations are actually mobile. So you see here a segment of a dislocation which moves through this sample, and then another one and another one. This has happened when you strain the sample. This is actually silicon, where this is seen at high temperature. And you also see that sometimes the dislocation mobility direction change, so it's actually quite complicated, these effects where dislocations move and interact with each other. This is from a French site from the University of Toulouse, which has a website which has really nice animations of dislocations, both experimental and simulation images of dislocations and dislocation mobility. Well, if we go a bit more detail into what the dislocations actually are. So dislocations, there are two basic type of geometrically simple dislocations, known as the edge dislocation and the screw dislocation. And in this case, conceptually, you can imagine that you have a crystal or where you first slip one upper part to the left, right, lower part to the left in this image, but then leave one part unslipped. And when you drag out the atom planes on one side and compress them on one side, you realize that some places the atom planes break, and then you can have a feature like this, that you have one atom plane on the upper side which is missing on the lower side, and this is the dislocation edge, and the dislocation line goes through the crystal in this direction. The screw dislocation, by contrast, is done by a similar thing, except that you, instead of having the left and right part slipped, you have the in the length direction upper and lower part, or however you may call it, another part slipped. And then in that case you realize that you will here have a feature where the atoms planes are slipped, and here have a mismatch in the atom planes. And this, on the atomic level, this is maybe even easier to understand. So an edge dislocation simply looks like this. So an extra atom plane which ends, and then the atom planes around it curve. So now this here is the dislocation core, well, it's a little bit of a matter of definition, but you could also call the dislocation core, say, the atoms closest to the center, but the dislocation line itself is here at the center, so the dislocation line does not consist of atoms, it's just a line which follows this place where you have an imperfection in the crystal where you have a lattice plane ending. The screw dislocation is a little bit more difficult to visualize, but this is showing how the atom planes bend over it. And the reason for this name screw dislocation is that if you start somewhere here and follow the atom planes at the nearest neighbor distances here, you realize that you will, if you do this following, you will get in 3 dimensions a screw-like pattern, which gives the name screw dislocation. And these are the geometrically simple types of dislocations. And in reality, dislocations may not be this simple. They can be a combination or something in between line and screw dislocations. And this, that it can be in principle any, can be understood by this talked experiment, Gedanken experiment. Which say that, okay, you take a perfect crystal and then you select an arbitrary surface. This can be of any shape inside the crystal, and then remove the material on one side of the or cut. You can imagine that we cut all bonds along this surface, and then move all the atoms by some vector b on then. And then you create some empty space and you fill this empty space with new atoms, or if B is in the opposite direction, you press atoms on top of previous atoms and then remove the atoms which were pressed on top of previous atoms. And this can in principle be done for any surface and any vector B. But in reality, many of the things would be extremely high in energy and thus in practice not form. Then the easiest way to form this, to be sure that you sort of have a low energy structure, is that you take B to be some, for instance, the nearest neighbor interatomic distance, and fill the atoms such that along this surface you actually have perfect crystal. In this case, along this surface, the atoms are in the perfect equilibrium state and there is no energy associated with it. But here where you broke the structure, there of course you will have this dislocation line, and this dislocation line will then have some energy because the crystal structures are broken. But when you plot it this way, you realize there is no reason it has to be edge or screw along this line. It can be anything, any crystal direction, which doesn't have locally any simple atomic structure explanation. Well, if you fill it in a way that the crystal structure is not perfect, then it's not a perfect dislocation, then it's called a partial dislocation. And to do this, there is an illustration of how this can be done in the simplest possible two-dimensional lattice, the quadratic lattice. So here we have the cut points. In 2 dimensions, you wouldn't have a dislocation line, you would have a dislocation point. And then you move all these atoms here one step upwards along this vector B. And then after you have done it, you fill it with an extra atom plane in here. And then you have created a dislocation points in 2 dimensions. These 2 points are dislocation points. But now if you imagine repeating this in or out of the plane in a 3-dimensional simple cubic crystal, then you have created a dislocation line. Well, you also realize that when you do this, that the atom bonds here are stretched, and this is perfectly true, and the way this is drawn, you would have a pretty high strain here as well, but in reality, usually this strong distortion is local around the dislocation core, a few atom planes maybe around the dislocation core. But in principle, it has an infinite range, because once you have an extension or compression in a crystal, this will, by elasticity theory, the strain field will extend to infinity. So this vector B is crucial for understanding and describing dislocation properties, and it has a well-defined name. It's called the Burgers vector. And here is a nitpicking thing. This Burgers vector got its name by a Dutch scientist known as Jan Burgers. And note the name actually has an S in the end. So this Burgers vector is not a genitive. It's the name of the, Mr. Burgers, who once upon a time described this for the first time. So this defines the simplest dislocation. And if you have a dislocation that ends at the surface, it's actually a matter of definition whether you say that added atom row or removed one. So in this case, you can imagine that here, either that here we added a one atom row, or at the bottom that we removed one atom row. And in this case, it's actually impossible even to define whether you added or removed if you only know the end result. But if you have a finite loop, like those shown in the earlier images, then you can make a distinction whether atoms were added or removed. And if atoms were added, then you call it an extrinsic dislocation or an interstitial type dislocation. And if atoms were removed, then it's called an intrinsic dislocation or vacancy type dislocation. Note that the words of extrinsic and intrinsic are here used in a different way for point defects. For point defects, extrinsic meant impurities, and intrinsic defects with only the same element. But here it's extrinsic means more atoms, interstitials, and intrinsic means less atoms, vacancies. Well, and if you have any dislocation, you can conceptually define a Burgers vector with the following operation. If you look at this crystal, at first it looks perfect, but if you look very carefully, we actually want to tilt the plane. I won't tilt the screen now, but if you can tilt your screen, it may be actually easier to see that there is actually an extra atom row here, which ends somewhere around here in this system. So you may, if you try to follow the atom rows here, I mean, here you see that this would be one atom row. Oops. But then on here you would have one atom row clearly, but in between you see that here we would have one atom row, and here you notice now they don't match. Now here in between here is an extra atom row. So to deduce the Burgers vector, what you do is that if you know where your dislocation core is, take some atom fairly far away from it and start going in one or the other direction. So here, if we start from first from atom A down here, what we do here is move downwards left 1, 2, 3, 4, 5 times. Then we move to the right 1, 2, 3, 4, 5, 6 times. Then we move upwards to the right 1, 2, 3, 4, 5, and then left 1, 2, 3, 4, 5, 6 times. You see that we ended up at the same atom where we started. And this is now imperfect crystal, so it's very natural. But now if you do the same around the dislocation core, what will happen? Okay, from B we move 5 steps left downwards, 1, 2, 3, 4, 5. Then we move 6 steps to the right, 1, 2, 3, 4, 5, 6. Then we move 5 steps up the right, 1, 2, 3, 4, 5. And now we move 6 steps to the left, 1, 2, 3, 4, 5, 6. And you end up at atom C. So now you see you started at atom B, but you didn't end up in the same atom B, you ended up at atom C. And this is of course because there was the extra atom plane in here and the dislocation at the center. So this means that this circuit is now not closed. And this means that there must be a dislocation there, and the difference between the positions, atom positions B and C, define the Burgers vector. The sign is arbitrary. You could do this the other way direction. You could get the same vector, but in the opposite direction. So the sign is not meaningful. But this actually defines a dislocation. If you do this Burgers circuit operation, if you do it in perfect crystal, you get B equals 0 because you end at the same atom. If you do it around a defect and you end at the same atom, then it's not a dislocation. So the Burgers vector really can be used to define what is a dislocation. And this is an important distinction because not all line defects are a dislocation. Imagine taking vacancies, taking say here removing this atom and all atoms above and below it in a three-dimensional crystal. Then if you do the Burger circuit, you would get B equals 0 because the lattice is not distorted. You don't have any extra atoms around, extra atom planes in or around it. So a long line of vacancies is definitely a defect, but it's not a dislocation. So, well, this was the traditional historic textbook theory, and which is of course still correct. But now it's worth mentioning in a modern course that doing this by computer simulation numerically had a big advance around 2010 and 2012 when Alexander Stutkowski and Carsten Albe from Technical University in Darmstadt in Germany developed an algorithm to determine the Burgers vector from atom coordinates. And in principle, what they did is exactly what's the definition of Burgers vector, but it's actually not so easy to do at all automatically in a computer, because you need to be able to define where the dislocation core, what are defective atoms, and then form this circuit. But this dislocation extraction algorithm does it, and it allows, if you have atom coordinates in here, what's been done is that first you analyze which atoms have somehow imperfect neighborhoods by knowing sometimes as CNA analysis, coordination neighbor analysis. And then once you have done this, you construct the Burgers vector around this and then define a line-like segment which shows where the dislocation is. And this actually works for quite complicated dislocations. So one can create complicated dislocation networks like here, and then define what the Burgers vectors are for these. And then note that this also both work for perfect and partial dislocations. So in this case, here you see that these planes here are the core of one partial dislocation where atoms are not at perfect neighborhoods, and then this analysis gives the structure of the partial dislocation, and in other places you only have perfect crystal, and then it gives the structure of the perfect dislocation. So the Burgers vector is first of all important to know, and also it's important to know that it's now possible to detect it also in computer simulations. The key software where this is implemented is a software called Ovito, which has an open source version and a commercial version. Well, now it might be a good point to mention that what are these possible partial dislocations surrounding. And the by far most important type of two-dimensional defect associated with partial dislocation is known as stacking faults. And this standard example of this is in the FCC metals. If you remember from your basic crystallography studies that an FCC metal can be understood as a number of closed-packed 2D hexagonal plates which are stacked above each other as ABC, ABC, ABC stacking, whereas an HCP crystal is formed by putting the same hexagonal layers in the AB, AB, AB stacking. If you have hard spheres, the energy of these two crystals is actually identical because this is just a matter of packing hard spheres. So if you change the stacking sequence, it likely won't actually have a big effect on the energy. And this is true, and because of that, stacking faults are relatively easy to form, both FCC and HCP metals. So for instance, in FCC, if you do change the stacking sequence from ABC, ABC, ABC to ABC, AB, AC, always you have to make sure that two letters are not next to each other. That would have a high energy because then atoms will be on top of each other and can easily glide next to each other. But if you insert a plane so that no two letters are repeating, this has a fairly low energy defect. It's still a defect because it's not the perfect stacking sequence, and it will have higher energy, but the energy difference may be quite small. And if this stacking fault is local inside a crystal, then it's a planar defect which is surrounded by partial dislocations. Because obviously, if you do a Burger circuit around a fault like this, the directions will change, and you will have a Burger vector which is non-zero. And also, the stacking faults can also be formed in silicon and diamond structure crystals. Because if you remember, a diamond structure crystal is two interpenetrating FCC lattices. And it can be written as large A, small a, large B, small b, large C, small c, and so on, stacking AA, BB, BCC. And then you can here insert a stacking fault by putting in a double layer, extra double layer. And the reason it's important to put a double layer is that by doing a double layer, you can ensure that all atoms in the stacking fault core still have 4 bonds. And this is illustrated in a structure here. This is here the red and blue atoms are the large A, small a layer. So blue can be considered as large A and red small a, or vice versa. And then the atoms surrounding it are the regular atoms. In here at the center you can form this so that all silicon atoms still have 4 bonds, because most of the bonding energy in silicon, almost all the bonding energy is the nearest neighbor bonds. You realize that the stacking fault energy is quite low. But then at the edges of the stacking faults here and here, you will have a partial dislocation line. So dislocations, as said, can be given as number per area, and dislocation densities in typical metals have a wide range of values. In a very high quality crystalline metal, crystalline, not polycrystalline, but anyway high quality crystal, the dislocation densities are of the order of 1000 dislocations per square millimeter. And this is actually a very small number, because remember, you start one dislocation core is less than a nanometer. So 1000 nanometer square size defect over a millimeter is actually a very low number. On the other hand, then if you have a heavily deformed metals, heavily deformed means, for instance, that you take a metal and start banging on it with a hammer, and when you bang on it with a hammer, you actually increase the dislocation density. And if you do it heavily, you can get to dislocations of the order of 10 to the power of 10 per millimeter squared. And this is actually, remember, this nanometer size, this actually starts to be a quite large number of defects, even considered from the atomic scale. 1 millimeter squared would of course be 10 to the power of 10 to the power 12 nanometers squared. So you realize that you would have, for every 10 nanometers, you would have a dislocation line. But then, as said, irradiation can generate dislocation loops, and one can get them up extremely high densities. If you assume that we would have heat spikes, all of which create dislocations, which could be possible, for instance, in heavy ion irradiation of tungsten, and then one will get a dislocation density as high as 10 to the power 11 over square millimeter. And if you radiate for long, this could become the global dislocation density, unless the dislocations migrate and grow, which they quite often actually do. Well, and this dislocation mobility is also a key aspect of dislocations. And this is why they are so important for the mechanical properties of metals. And the reason to this is that dislocations actually, in certain crystal directions, they're actually very, very easy to move. The reason to this can be understood going back to this schematic illustration, edge dislocation. Here you have an edge dislocation. One often has this perpendicular notation for it. And here you realize that to move this dislocation core, The only thing you need to do is to move it one step to the left is that you break these bonds and form new bonds here. But to do this, each atom actually needs to move much less than one intraatomic spacing. And also this bond breaking operation in a metal which doesn't really have covalent bonds is actually very easy to do. So because of this, the dislocation movement it actually can be very easy in a well-defined crystal direction. You also realize from this image that if you would want to move the dislocations, for instance, in this direction, this would be quite difficult because it's not obvious at all how, you would break and reform the bonds. To do this, you would actually have to move these atoms somewhere away, which is horribly hard. Dislocations which have an easy to move direction, they are called glissile, they glide easily, and others are called sessile, which means that they don't move easily. And this is actually already what I was saying, that it's easy to understand, it's easy to move here, but for instance, this operation would be quite difficult to do and hence extremely unlikely to occur. And those directions of crystals where it's easy to move dislocations are called glide or slip directions, and the planes where it occurs is a glide or slip plane. Because we're talking three dimensions, you always have a glide plane. The combination of the glide direction and the glide plane is called a glide system. And for instance, if you look at FCC, because FCC can be understood to build of these hexagonal close-packed two-dimensional 1-1-1 planes, it's pretty easy to understand that glide of an edge dislocation can occur perpendicular to the 1-1-1 plane, and then to get from one atom position to the next in this one, you would move in the 1-1-0 direction. So you would have a movement would be in 1-1-0 direction, and the plane would be 1-1-1. If you want to form a partial dislocation or stacking fault, then the movement would be another 1-1-2, for instance. And so that's pretty easy to understand. In other crystals, it's not so obvious, but here is anyway a summary from the textbook Callister about what are the most common observed slip planes and lip directions. So in FCC, it really is the 1-1-1 plane and 1-1-0 direction which are dominant. There are 12 crystallographically equivalent or symmetric directions to do this. Then in BCC there is a number of ones, but they are not quite as easy to move. And then in HCP there are also several ones, but there are less of them. And because slip is particularly easy in FCC metals generally are fairly soft, especially like gold and silver. You know that they are, if you are pure gold and pure silver, they are quite soft metals. Especially pure gold is actually extremely soft. That's why, for instance, jewelry is never pure gold, because you don't want to have that soft metal. And then you know well that iron is not so soft, and then these HCP metals are generally quite brittle if they are pure, and this is associated with it being more difficult to move dislocations in these HCP systems. Dislocations can also interact and react to each other, because you have this strain field around the dislocation, and this strain field, as I said, goes in principle to infinity. But for an edge dislocations, you realize quickly that here you have a compressive strain because atoms are packed together. Here you have tensile strains because there is some loose space here. So this means that you have compression on one side, tensile on the other, and this is actually very much like an electric dipole. Plus on one side and minus on the other. And it turns out that the strain field, the analytical equations for the strain field even resemble those of the electrical dipole. And now you can understand some simple possibilities of dislocation reactions. If you have two edge locations oriented the same way, then you have a compressive strain here, tensile strain here, tensile strain here. These would naturally repel each other. especially for the compressive, it's easy to understand. You don't want to compress the crystal even more. But then on the other hand, if you have their opposite direction, then you have compressive here, tensile here, and this would naturally attract each other. We call plus and minus, and here it's the opposite, and this means that these two are attracting each other, and if they are on the exact same plane, they can meet and annihilate, and you're left only with perfect crystal. And this is actually also very analogous to electric dipoles. So the electric dipole, of course, also attract each other if it's oriented like this, and if it's oriented on the same direction, they repel each other. And due to these strain field interactions, dislocations can actually be modeled as a set of interacting line segments, there is a simulation techniques which simulates the motion of these line segments, known as discrete dislocation dynamics, or DDD. The basic idea is similar to molecular dynamics, but instead of moving atoms, you are moving dislocation segments. And this is something which then allows really modeling efficiently dislocation motion. And here is an example of a simulation of a Frank Reed source, which means you have two hard defects around here, and then put this crystal under strain or tensile strain. You elongate the crystal in this direction. If this happens, then you can get something like this, a source of dislocations, which keeps creating dislocations out from this system. And as you see, it can repeat itself in principle forever, as long as you keep straining the crystal. This particular simplest possible dislocation source is known as the Frank Reed source. Then dislocations slow down each other's motion, and this is illustrated here, where you have one Frank Reed source, but then number of small immobile dislocation segments. They are assumed to be immobile in this simulation. You see how the motion of the dislocation is affected by the segments. And this starts to be already related to radiation effects, because dislocation loops and other defects created by radiation can have exactly this effect. And this leads to the fact that, yes, irradiation has a big effect on the mechanical properties of metals, because you create dislocations which then affect the dislocations that normally would be in the metal. And this leads to the fact that, well, not in all, but in most cases, when you irradiate the metal, increasing dislocation concentration makes the material harder, elastically harder, which means that this elastic region in a stress strain curve keeps increasing. But at the same time, it makes it more brittle. That is, it breaks easier when you reach a critical density. In FCC, these effects are fairly strong. In BCC, they can make them irradiation can make metals extremely brittle but harder before it. And this is something which is quite crucial for the use of metals in irradiation environment. If you have an environment where the dose is not hugely high and you stay in this elastic region, this is sort of good news. You keep the metal from permanent deformation for a long time, but then it's also risky, because if you exceed the dose or the strain in the elastic region, then the metal may completely shatter, which especially if you imagine having a nuclear reactor, you really do not want your nuclear reactor to shatter. Well, the good news here is that you can remove dislocations. The basic idea for removing dislocations is simply heat it up, and that usually makes dislocations mobile, start reacting with each other, getting to lower energy states, and this means that you can recover the properties towards this equilibrium state. On the other hand, you can also have recrystallization, that if you have a poor quality crystal, the crystal quality improves, but at very much or long-term heating, the polycrystalline grains may grow, which may or may not be good news depending on what kind of application you have. And out of these stages, this first stage is really defect removal, removing dislocations and other defects. Two letters then mean that dislocations are mobile, and the entire polycrystalline grains may change the properties. This concludes this first part, the sort of general dislocation part of this section 9 of the course.